In this chapter, we want to look into what is called complex number loci. What is a loci? Loci is the plural form of the word locus. A locus means a set of points that satisfy a condition. In this chapter, the condition that we refer to will be complex number equation or complex number inequality. And the way to go about this chapter is we have to first and foremost understand four fundamental expressions and then their geometrical interpretations. What are the four expressions? 1, 2, 3, 4. For the first one, this refers to the distance from origin to the complex number z. Right, so if you have a complex number z, modulus of z refers to this length. It also therefore means the distance from O to the complex number z. For the second expression, z minus z naught. Let me represent z naught as here, as a directed line like a vector, and z as here. Of course, z naught is a complex number that sits here, and z is a complex number that sits here. So where is this complex number z minus z naught? Like vectors, the complex number z minus z naught is here. Right, here. Okay, can you see it's like vectors? First vector and the second vector. When you take second minus the first, it refers to the vector here. So complex number and vectors, they are quite related in some sense. Some of the ideas that we know in vectors is actually borrowed and used here. So you have this complex number z minus z naught. Modulus of z minus z naught will therefore refer to this length. So as seen from this diagram, this length is as good as the length or the distance from z naught to z. So this is the second expression. In the third expression, we want to understand what does it mean by argument of z. Argument of z refers to this angle here. The angle that the complex number z made with the positive real axis. This is the argument of z. So this is the third expression. And for the fourth one, argument of z minus z naught. Now, once again, referring to this diagram, this is the complex number z minus z naught. The argument of z minus z naught is actually this green angle here. This positive real axis is actually translated to sit here, and the argument of z minus z naught is actually this angle here. So here we are, we have four basic geometrical interpretation for these four expressions. Now with this, we are now ready to look into what is called basic loci, and we will introduce the four basic loci here. For the first one, this is actually a complex number equation. Why is it so? Because it's a complex number. In this equation, what we see here is on the left, it is the modulus of z, and modulus of z refers to the distance from O to a complex number. On the right, if this is a numeral, okay, this refers to a numeral. So taken together, it means the distance from O to the complex number z is always r. So where are these complex numbers z that will satisfy this condition? Bear in mind that the distance from O to the complex number z must be r. From O to the complex number z must be r. And you find that actually all points on this circle will actually satisfy this equation. That the distance from O to the complex number, O to the complex number, O to the complex number, they all have a modulus, in this case, or the length r. So therefore, if you have understood the basic interpretation, when put together here, you realize that actually this equation represents locus of points z that sits on the circle, center O and radius r. And we describe this locus as a circle, center at O with radius r. So this is the first basic locus. For the second locus, we have modulus of z minus z naught equals r. In this expression here, I want you to know that this z naught represents a fixed complex number, whereas this z represents a variable. So what we are looking here is complex number z that will satisfy this equation. So what we are looking here is complex number z whose distance from z naught to z, this represents distance from z0 to z is equals to r. So in this diagram, if this represents z0, we want all complex number whereby the distance from z0 to z is r. So if you have a complex number z0 here, then potentially this point can be z, where the distance from z0 to z is r. This point here can also be z because the distance from z0 here to z is also r, and so on and so forth. So by such argument, based on the basic interpretation, you would come to a conclusion that this complex number defines a circle centered at z0 and the radius is r, because all points on these circles, they all satisfy this condition, which is the distance from z0 to these complex numbers, they all have a distance of r. And we describe this locus as a circle centered at z0 with radius r. And now it comes to the third one. Argument of z equals to theta. The argument of z equals to theta represents a locus which is called a half line. Now, a half line is something that is terminated at one point and goes on forever in the other direction. If you have a line goes on forever, right? If you have something that terminates at both ends, well, this is a line. This is called a line segment. A line segment. So what we have here is a line segment. This is a half line. So I want you to understand that a complex number equation argument z equals theta actually represents a half line starting from the origin O and making an angle of theta. Why is that so? Because all points, say maybe at the point here, say for this point here, all points, say for a point here with, and I call this point complex number z, right? For a complex number z sitting at this point, you realize that the argument of z is indeed theta. And by a similar argument, you can argue and conclude that all points along here will have an argument of theta. Therefore, all points along this line satisfy this equation. And you know that this is only true for points on this side. If you have points on the other side, of this so-called line, points on the other side of this line will not satisfy this equation, because if you have a point that's along this side, right, then the argument is actually here, and it's no longer theta. You know what I mean? If you choose point that's along the same line but it's on the other side, it won't satisfy this equation, because then the argument will be something like this. Right, let me just put it down in green color. Imagine if you're talking about points, say, along here. It won't be correct, because then these points, their argument will not be theta, but something much bigger and in the other direction. Right, let me erase it off. Okay, so number 3 represents so-called a half line. And then for number 4, if you have argument of z minus z naught, this again is also a half line. In this case, the half line starts with z naught. If this is origin, this is a fixed complex number z naught, right? Fixed complex number z naught. From this point, you will draw so-called a half line, and this half line makes an angle of theta with the positive real axis. Now this dotted line is parallel to this dotted line, so you can think of this dotted line as the positive real axis shifted up here. So now you want to give a little bit of explanation why should it be that points along this line will satisfy this. Sorry, I missed out something. Please let me put in theta. Let me erase off and put theta. This equals to theta as a half line. Right. Okay. So why do points along this stretch here satisfy this equation? The way to think is like this. Let's take a point, say here. So this is a complex number z. This is a complex number z naught. So where is the complex number z minus z naught? Like what we have argued over here, right? If you have a z here and a z naught here, then z minus z naught will be here. And it's not hard for you to see that a complex number here, which is z minus z naught, has an argument of theta. So by this argument, this point therefore satisfies this equation. And you can repeat the same argument for a point here, for a point here, for a point here. In fact, for all points along this stretch here, they will all satisfy this equation by the same argument. If you try to look at points below, you find that they will not satisfy this equation for the same reason that points over here don't satisfy this equation. So therefore, what we have here is in case 4 or in the fourth basic locus, you have what is called a half line, but this half line starts from z naught. Let me now erase them to reinstate the diagram. Okay, to give a more complete description of these two half lines, I want you to actually look at the writing here. Okay, to describe them in more completeness, for number 3, argument of z equals theta is described as half line starting from O and making an angle of theta with the positive real axis. And for number 4, this is fully described as a half line starting from z naught, making an angle of theta with the positive real axis. So with this discussion here, I've laid down the background and the basic knowledge you need to bring yourself through the entire chapter 3. For the rest, we will discuss them in the notes in the class. Thank you.